Have you ever stopped to think about how we make electricity? Not with batteries, not with a wall plug, but from scratch. How can simple motion, something as basic as spinning a wheel, end up lighting an entire city? Well, today we're diving into the incredible, invisible force that makes it all possible: electromagnetic induction. Let's get into it. Okay, picture this. You've got a loop of wire. That's it. You connect it to a meter that can detect current. Now you take a simple magnet and just move it near the wire, and bam! The needle on the meter jumps. You've just created electricity, seemingly out of thin air. But it's not magic, it's pure physics. And this one principle is behind pretty much all the power we use every single day.
So that really is the central mystery, isn't it? How can moving a wire through an invisible magnetic field create a very real electric current? Well, the answer lies in a couple of beautiful rules figured out way back in the 19th century.
To really get a handle on the rules of this game, we first need a way to talk about that invisible magnetic field. And for that, we use a concept called magnetic flux. You can think of it as just a way of counting how much magnetism is passing through a certain area.
Right, so magnetic flux, we use the Greek letter phi for it, is basically our measurement of how many magnetic field lines are poking through a surface. The more lines that go through, the higher the flux. We measure it in units called Webers. And here's the kicker. It's the change in this flux that's going to generate a voltage, or what scientists call an electromotive force, or e.m.f. for short. But, and this is super important, the angle is everything. If you hold your surface, let's say a loop of wire, face on to the magnetic field, you get the absolute maximum flux. It's like holding a net perfectly in the wind. But if you turn that loop sideways, so the field lines just skim right past it, the flux passing through it drops to zero. It's all about how many of those lines you're actually cutting through.
Now, in the real world, a single loop of wire is okay, but coils with tons of turns are way better. And that's where magnetic flux linkage comes in. It's actually really simple. You just figure out the flux for one loop and then multiply it by the number of turns, which we call N. More turns equals more linkage, and more linkage means a much bigger effect.
And this right here, this is the main event, discovered by the legend himself, Michael Faraday. And the most important part of this whole idea is the phrase rate of change. It's not the amount of flux that matters. You could have a huge magnetic flux sitting there, but if it's not changing, absolutely nothing happens. The magic is in the motion, in causing that flux to change over time.
Okay, that's enough theory for a minute. Let's make this real. It's time to crunch some numbers and see how these ideas play out in a practical example.
So here's our setup. We've got a coil of wire with 400 turns. Its radius is 3 centimeters, and it's sitting in a pretty beefy magnetic field of 1.4 Tesla. Our job is twofold. First, calculate the magnetic flux going through just one of those loops, and second, find the total flux linkage for the entire coil.
The process is actually pretty straightforward. First things first, we need the area of our coil, which is just some high school geometry, pi r squared. Once we have the area, we multiply it by the magnetic field strength, B, and that gives us the flux for a single loop. Finally, to get the total flux linkage, we just multiply that result by the 400 turns in our coil.
And there are our answers. The magnetic flux is about 4.0 milliwebers, and the total flux linkage comes out to 1.6 Weber turns. But remember, this is just a snapshot. This is the value at one specific moment. The real action, the electricity, starts when this number begins to change.
Okay, so Faraday's law tells us that a changing flux will create a voltage. But which way does the current flow? This is where the story gets really interesting, with a fantastic plot twist called Lenz's law. Lenz's law is one of my favorite ideas in all of physics because it's so stubborn. It basically says that nature fights back. Any current you create will always flow in a direction that creates its own magnetic field to oppose the very change you're trying to make. It's like the universe just doesn't like being pushed around.
And this shows it perfectly. If you try to shove the north pole of a magnet into a coil, the coil gets annoyed with that increasing flux. So what does it do? It creates a current that turns its own face into a north pole to push your magnet away.
Then, if you try to pull the magnet out, the coil says, "Oh no, you don't," and flips its polarity to a south pole to try and pull it back in. It always fights you.
So when you see the full official equation for Faraday's law, you'll see a little negative sign out in front. That's not a mistake. That tiny minus sign is Lenz's law. It's the mathematical way of saying that the induced voltage, E, will always be in the opposite direction of the change in flux. It's the symbol for that cosmic stubbornness.
Now check this out. You don't even need to be moving a physical magnet around. If you just have two coils sitting next to each other, and you start changing the current in the first one, coil A, well, that changes its magnetic field. That changing field then passes through coil B, which induces a current in it. They never even have to touch. This is the magic behind every single transformer in the world.
All right, so we've got these incredible laws of physics, but what are they good for? Let's take a look at how we've taken this invisible force and literally built the modern world with it.
The biggest application, by far, is the electric generator. It doesn't matter if it's powered by a steam turbine, a waterfall, or a wind turbine, the core idea is exactly the same. You use some force to spin a massive coil of wire inside a magnetic field. As it spins, the flux linkage is constantly changing, from max to zero to max in the other direction and back again. And that continuous change, thanks to Faraday, creates a continuous alternating current. This is it. This is how we power the planet. But induction isn't just about making things go, we can also use it to make things stop. What you're looking at here is a system for eddy current braking. It's an incredibly clever, touch-free brake you'll find on things like high-speed trains and the biggest roller coasters.
So how on earth does that work? It's 100% Lenz's law in action. As a solid metal disc, like a wheel, spins through a super strong magnetic field, tiny little whirlpools of current get induced inside the metal itself. We call them eddy currents. And these currents create their own magnetic fields that, you guessed it, oppose the original motion, creating a really powerful braking force without anything ever physically touching. It's amazing.
So we've covered the laws and some incredible applications. Now let's really put our knowledge to the test with a couple of slightly more complex real-world problems.
Okay, for this one, we have a 200-turn coil just sitting in a magnetic field. Then we yank it completely out of the field, and we do it fast, in just 0.24 seconds. The question is, what was the average voltage that we generated across that coil while we were moving it? Let's walk through it. First, we figure out the total flux linkage when the coil is sitting inside the field. That's our starting point. The final linkage, well, that's easy. It's 0, because the coil is outside the field. The crucial step is to take that total change in flux linkage and divide it by the time it took for that change to happen, which was 0.24 seconds. That's Faraday's law in action. And when we do the division, we get 0.03 volts, or 30 millivolts. So just by pulling that small coil out of a magnetic field, we actually generated a real measurable voltage. All right, prepare to have your mind bent a little. Did you know that an airplane, just by flying through the air, basically turns into a generator? Let's figure out how. Just think about it. The metal wings of a plane are just a giant electrical conductor, and they're moving incredibly fast through the Earth's own magnetic field. As they fly, the wings are sweeping through a huge area every single second. This constant sweep means there's a constant rate of change of magnetic flux. And what did Faraday tell us? A change in flux must create a voltage, in this case, across the wingspan. And if you actually run the numbers for a typical flight, you find that a voltage of about 54 millivolts is generated between the wingtips. It's not a lot, but it's a real, measurable electrical effect caused by just flying through the sky. And because of some other physics rules, we even know that the right wingtip will be the one with the higher voltage. How cool is that? Okay, we have covered a ton of ground. To make sure all these ideas are really locked in, let's wrap up with a couple of quickfire exam-style questions. Let's look at this first one. The question is, which of these things will make a smaller induced voltage, or e.m.f? While we know the voltage depends on the rate of change of flux. Reversing the movement or the field just flips the direction of the voltage, not its size. Moving the wire quicker would actually make the voltage bigger, so the only option that reduces the effect is D, using a weaker magnetic field to begin with.
Okay, next question. This one is about transformers, a perfect application of induction. The key here is the phrase 100% efficient. That means the power going into the transformer is the same as the power coming out. The lamp uses 12 watts of power, so the supply must be providing 12 watts. We know power is voltage times current, so if the supply provides 12 watts at 24 volts, the current is just power divided by voltage. 12 divided by 24 is 0.5 amps. The correct answer is A.
So let's just step back for a second and appreciate the journey we've been on. It all started with something as simple as a twitching needle on a meter.
We saw that a little bit of motion and a little bit of magnetism can somehow create electricity. And then we uncovered the elegant rules that govern how it all works. Faraday's law, which tells us that change is everything, and Lenz's law, which shows us how nature always pushes back.
And what's so incredible is that these two simple rules aren't just lines in a physics textbook. They are, without exaggeration, the foundation of our entire modern world. They explain the giant generators that light up our homes, and they explain the futuristic, frictionless brakes on a high-speed train.
Learning to harness this invisible force of electromagnetic induction completely changed the course of human history. Which really makes you wonder, what's the next invisible force out there, just waiting for someone to notice a little twitch, ask the right question, and change the world all over again?